All right, so looking here, development of the model, kind of reviewing from last class where you did the kind of the explore activity. We're just going to touch on a few things. What you should be able to do is compare and contrast the historical models of the atom from that standpoint. Discuss how the development of the modern atomic theory reflects the nature of science. So basically how they built upon each other as it went. We went through matter is composed of tiny particles called atoms. That idea never existed a few thousand years ago. They didn't have much technology either, so I mean it's reasonable. Matter could be divided into smaller and smaller pieces. To go from there, Democritus, being a Greek philosopher, he's actually the one that came up with the word atomos, which is where the word atom comes from. And you know, he really was thinking about how they must be small, solid, homogeneous, indestructible particles. First person to propose that matter's not infinitely divisible. Believed atoms could not be created, destroyed, or further divided. Now this part we do know is incorrect because we can further divide them into their subatomic particles, but they do not retain the properties of those elements when you do so. And of course, his ideas are rejected. Obviously, not a lot of technology and no way to prove that. All right, Dalton also didn't have a lot of technology or a lot of experimental data, but he did think about things and study. So the modern atomic theory really starts with John Dalton. And he also thought of the solid sphere model like Democritus. All matter is composed of extremely small particles called atoms. And he thought that all atoms of the given element are identical. So that's one of the main points of Dalton's theory. Same size, mass, chemical properties, you know, but each element had their own specific size and mass and all of that other thing. But we know that they're not all, even atoms of the same element are identical. And we'll be able to prove that one wrong now. He also believed in like the law of conservation of mass where it's not created or destroyed. But once again, divided into smaller particles, this is possible, even though it won't retain the properties of the element. It will just end up being, you know, the subatomic particles. Conservation of mass, chemical reactions, they are separated, combined, rearranged. He did a lot of, they would rearrange in small whole number ratios and things like that. So there's a lot of points that he thought about, and most of them still hold true. A couple of them don't. The dividing into smaller particles and the being identical for every element. Thompson, did his look like? Well, if you looked at and comparing, they were solid sphere. Thompson's was called the Plum Pudding model, so we're going to take a look at where he got those ideas from. And he did this cathode ray tube experiment. Hopefully you got to see it in the PhET simulation, where he had the positive plate, the negative plate, and he sent stream, you know, of high voltage through. As you can see at the time, he didn't know that they were electrons, but these particles, they all kind of veered towards the positive plate. The positive plus the negative, of course, opposites attract idea. So basically through this experiment, he discovered the electron, which is important, okay? Didn't call them electrons, but these negatively charged particles, he is given credit for discovering them. And so he came up with his plum pudding model, which we don't really use plum pudding, or I don't think it's something that's like regularly eaten in our society anymore. So I kind of like to think of it more as an M&M blizzard, where you have the ice cream and then you have the M&Ms floating throughout. But that's the idea. The pudding part was like the ice cream, and then the electrons were like the plums floating throughout. So it's this positive medium with the electrons floating out. And so that was a good step in the right direction. Millikan, although wasn't really discovering, you know, the actual model, he did discover the charge of the electron through his oil drop experiment. And if you have time, you can take a look at the experiment here. I put a link. It's a really good short video, and if you really like physics and electric fields, you'll think it's really cool. But from finding the charge of the electron, he was able to calculate the mass of the electron, which is very small. It's very, very small, 10 to the negative 28, small number. So we do give him credit for discovering one of the subatomic particles. Didn't really talk about him in the slides on Thursday, but it's just another fun fact. Then Rutherford did make huge gains in the atomic model. His experiment, though, was called the gold foil experiment. And let's see the setup here as we put it on the screen. So he had it set up with this radioactive substance here because he's going to shoot alpha particles at the gold foil. Alpha particles are a type of radiation which we'll learn more about in nuclear. They do have a positive charge. They're basically helium nuclei. And when he shot them at the gold foil, a lot of them went through, a few of them bounced off. And then he recorded, the amount that bounced off. So the ones that went through to the original screen, but you can see some of them deflected, some of them, bounced backwards. So most of the particles passed through, and he concluded from that the atom is mostly empty space. Then, the ones that deflected or bounced back, he determined that there must be some kind of positively charged dense nucleus there where the alpha particles would repel the positive nucleus because they're positive as well. Positive, repel each other. And that there's a dense, small positive center to these atoms. So that was the conclusion. Particles passed through, mostly empty space. The ones that bounced back gave up that small, dense, heavy, where the protons are. Now, he didn't discover, that they were protons, but he decided on this idea of the nuclear model where there was a nucleus and then the electrons were outside the nucleus. There are some other ones we're going to talk about later, like Bohr and Schrödinger, because those ones, are more about the quantum model and getting into the electron side of things. And today we're really going to stay focused more on the nucleus. And here comes the fun review stuff. Can you differentiate between a proton, neutron, and electron in terms of the size, composition, charge, and location in the atom? Determine the mass number and atomic number. Determine the number of protons and electrons in an atom. And differentiate between atoms, ions, and isotopes. So some new words maybe, or words that you heard in 8th grade that you'll need to review here. So what is an atom? The smallest particle of an element that retains the property of the element. So we have a gold ring here, and we break it down into gold dust. As long as, we haven't broken it apart into its subatomic particles, it's going to retain those properties of gold. Okay? So if you get further, though, where you're breaking it up into protons, neutrons, electrons, which takes a lot of energy, it's not an easy thing to do, by the way, then it would no longer retain those properties and be other elements. Subatomic particles, you probably remember protons, neutrons, and electrons. And this is like the Bohr model of the atom here, so we're going to stick with that for now. And what you may not know, all of this information, the symbols we use, the locations, the relative electrical charge, you probably figured out from the simulation, no problem. And the relative mass, I'm going to also talk about the actual mass. So for the symbol, we use P+, locations in the nucleus, relative charge is a +1, and the relative mass is called 1 atomic mass units. And we use this U for atomic mass units. It's unified atomic mass units. It's based off of carbon-12. The neutron, we use a little, 0. It's also located in the nucleus, but we use the 0 because it doesn't have a charge. And its relative mass is also 1 atomic mass units. Now, the actual mass of a proton or neutron is about 1.6 times 10 to, and there should be like a little caret there, to the negative 24 grams. So super small. But instead of making you do calculations with this ridiculous exponent number here, they, basically said this equals 1 atomic mass unit. So we're going with that. That's the equivalence here. For the electron, which the E minus is outside of the nucleus in the cloud, it has a negative charge, and it is basically 0. We say negligible. So a 9.1 times 10 to the minus 28 grams. That one's really even smaller than the proton or neutron, so we basically say it's 0 or negligible. Doesn't really play a factor here. Now the atomic number on the periodic table is always the whole number. Don't worry about the decimal one yet. We'll get to that on Thursday. That's the average atomic mass. The symbols and, of course, the element name is what you'll find here. But this atomic number is going to give you the protons. That's going to identify the element. So any atom, doesn't matter anything else about it, just so long as it has a one proton, it's automatically going to be a hydrogen. So say I said carbon is number 6 on the periodic table for atomic number, so it's always any atoms that have 6 protons are automatically carbon atoms. Atomic number equals the number of protons. Now, we're talking about atoms here, which are neutral. Then that means the number of electrons are equivalent because the positives equal the negatives. So when the positives equal the negatives, you are at 0 anyways. That's your net charge. Mass number. Technically, the mass should be everything in the atom, right? The electrons, the protons, and the neutrons. However, we just said that the electrons barely have any mass. It's negligible. So we kind of factor them out and not really care about them. The mass number, therefore, is going to be the protons plus the neutrons. So the number of neutrons, you can switch that around. If you have the mass number of the protons, you can subtract to get the neutrons. Or if you have the mass number in the neutrons, you can subtract to get the protons. So you can use that any way, shape, or form you want to. Now let's do some quick practice. I'm going to give you a couple minutes here. See if you can fill those in, get your periodic table out, and take a look there. So that went forward, but hopefully you found boron on your periodic table and that it was atomic number 5. Now here it's telling you the mass number is 11, but what do we know about boron's number of protons based on the information that's provided? Who can tell me? Yes, it has 5. Very good, because the proton numbers equal the atomic number. Now, how do we calculate the neutron number here based on the information we have provided about our boron atom? Mass minus protons, exactly right. Mass minus protons, that's going to give us our neutrons. So 11 minus 5 gives us 6. Now, since this is an atom of boron, we're saying the word atom, that means it's neutral. If it has 5 protons, then how many electrons must it have? Also 5, very good. So far, so good. Now, in the next row, they didn't give us the element. They did give us the atomic number, however. So I can figure out the element very easily by looking at my periodic table. Can anybody tell me what element we have here for atomic number 17? Yes, that's chlorine, exactly right. Once again, we can do the mass minus the protons in order to get the neutrons, and since the atomic number is 17, we know the protons are 17. So how many neutrons for this chlorine atom here? 35 minus 17? Yep, it's 18. Very good. And once again, we're talking about a neutral. These are all neutral, so how many electrons would this chlorine atom have? 17. Very good. All right, aluminum. What's aluminum's atomic number? Aluminum going once. Yes, 13. Very good. How do you figure out the mass number now? We know the atomic number is 13, so that means the protons are 13 as well. So how do we figure out the mass number? This is kind of the work backwards way here. We know neutrons, we know protons, so we add them together. Good. So that should be 27. Very good. Like I said, we knew that the protons were 13 because the atomic number is 13. So now the electrons, obviously, for a neutral atom of aluminum is going to be 13. All right, so this is the basics of atomic structure, going through the protons, neutrons, and electrons for an atom. Let's look at isotopes. In nature, elements are found as a mixture of isotopes. For example, hydrogen has 3 isotopes. We have protium, deuterium, and tritium. They're all different because they have different masses. If you look at protium, there's just the 1 proton, hence the name protium. And deuterium has a neutron and a proton in its nucleus, and that's why the mass number up here is a 2. And then last but not least, tritium, 3 particles in the center. That's where that tri comes from too. So 3 isotopes of hydrogen actually exist in nature. For example, there's also carbon ones, and the one that most people refer to is carbon-12. Carbon-12 is 6 protons, 6 neutrons, but carbon-13 is a very small amount of the isotope, And that would be where they have 6 protons and 7 neutrons, because that 13 gives an extra neutron. And carbon-14 you might have heard of before, because they use it in the radioactive dating, where you're dating fossils for living things. Its half-life is like 5,740 or something years. So it's a good one to look for dating. But 8 neutrons, 6 protons. So how are the isotopes different? Well, we're talking about different number of neutrons, and more neutrons means a greater mass. Now, atoms of the same element that have the same number of protons but have different number of neutrons, that's the actual definition of an isotope. Okay? What you need to remember about isotopes, that there are, like zinc has 5 isotopes, and they all have different masses based on their number of neutrons. But does that make the chemical behavior of one zinc isotope different than another? No, it actually doesn't. The chemical behavior doesn't really change about the isotopes, because that's really determined by the electrons. The electrons are the ones in the cloud. They're the ones that do the bonding, so they're the ones that are going to determine whether something will react or not. Isotopes really don't have anything to do with the chemical behavior of that particular element. Just wanted to point that out. Now, the isotopic symbol or notation. The A number in the upper left corner said this briefly on the last couple of slides, but this is going to be your mass number, and it's not going to be the atomic mass, because the atomic mass is the decimal number, so we're going to cross that part off. But it will be the mass number of that individual atom. The Z number down below is always the atomic number, which is of course equivalent to the proton number. And the X here, not the Z, the X is the element symbol. So I put a couple examples over here. If you're looking at this atom of neon, it has a mass of 20, and it has 10 protons. It's number 10 on the periodic table. I could easily subtract these two to figure out the neutron number, okay? This copper atom, based on this symbol, 29 protons, because all coppers have 29 protons. But it has a mass of 63, so you could subtract and also find the neutrons there. We're going to be using this kind of notation from now on. Isotopic notation also could have it written like this, where you have the name of the element dash, and this number over here is always going to be the mass number, like so. Okay, so pay attention to that kind of notation. You can also see it written like this, where it might just have the element symbol like C14, C13, that's also indicating the mass number. So need to use the periodic table here. We're going to look at carbon 12. All of the carbons have, our atomic number 6, so they're going to have 6 protons. And in this case, once again, we have not changed anything. These are all just atoms. There's no charge on them. We haven't looked at it in terms of ions yet anyways. So that means the electrons would also be 6. In this case, though, we have a mass number of 12, so 12 minus 6 gives us 6 neutrons. The only difference between carbon 13 and carbon 12 is going to be which particle here. Is it the protons, electrons, or the neutrons? Where are we going to differ? Protons, neutrons, or electrons? The neutrons, thank you, awesome, yes. So it's going to be 6, 6, but the neutrons, because this is carbon 13, is going to have one more neutron, so it's going to be 7. And once again, carbon 14 is going to follow that same pattern. 6, 6, because the proton number, the atomic number doesn't change for carbon, but this particular isotope, this particular atom is going to have 8 neutrons instead. This one's the radioactive one, though, used for carbon dating, by the way. All right, so let's do some more practice. I'm going to give you a couple minutes. Go ahead and get that done. Take a look here. Get out your periodic tables. Okay, so looking at our first example here. Has scandium. It gives us the symbol notation. So we see over here the 45 and the 21. And as you can see, the bottom number following the notation is the atomic number. So that makes the 45 the upper left corner which number? That's the mass number. Good. So that's 45. Now if the atomic number is 21, that means the proton number is also 21. Once again, figuring out mass minus protons should give us the neutrons. which happened to be 24, and then we don't see a charge on this, so this is going to be an isotope, which would be an atom of this particular atom of scandium, so its electrons would be also 21. Now for this gallium-60 here, what do I need to find on the periodic table about the gallium-60? On the scandium one, I didn't have to look at the periodic table because it was all told in the symbol. But here, I need to find something. What do I need to find? The protons, or the atomic number. Good. Did you find that one? How many were there? Yes, 31. Exactly right. Now, it did give us a piece of information. It gave us this dash 60. That's going to be which number? Very good. How many protons? 31. How many neutrons? 29. Very good. You guys did that right. The protons are 31, just like the atomic number, but when you subtract, you do get 29 neutrons. Exactly right. And then, of course, the electrons are the same. Here for the argon, it's the same deal. Find the atomic number on the periodic table. So that's going to be which number? Yes, 18. Very good. The mass number here is indicated to us 39. The protons again are 18 because that's the same as the atomic number. Subtract and we get 21 neutrons. So we subtract these. And then of course, if we have 18 protons, that means there's going to be 18 electrons in this case. The zinc one's similar to the first example here. The 30 is the atomic number, the bottom one. The mass number is the top left one, which is 65. So the protons must be 30. When you subtract the 30 from the 65, you get 35 neutrons, and then there's going to be the same number of protons as there is electrons because we have not been looking at this in an ion form yet. They have not gained or lost electrons yet. So this one's going to be 30. Speaking of ions, that's where we're headed. What is an ion? Okay, an atom that is electrically neutral, an atom. So atom is different than ion. Atom is going to be automatically understood as neutral. So that means protons equal electrons when we're talking about neutral or atom. Isotope is when they have different number of neutrons. So you can have an isotope and an ion at the same time, where you have different number of neutrons and you also have a charge. The ion part is when it gains or loses an electron. And this one example of a picture is showing that you're losing an electron here from this particular atom, and it's turning into an ion. Now, fun names, cation. That's how you pronounce this. I know I had a couple English people last year in my AP class that really hated the way that this is written, and it looks like cation, I understand that, but it's really pronounced cation. And the best way to remember cations is that it has a T in it, and the T means it's going to be the positive ion. Positively, that means it loses electrons. Now that's kind of opposite. You lose electrons, you become more positive because you're losing those negative charges. So looking here at our lithium, we could look up on the periodic table for our lithium atom. Does anybody see what the atomic number for lithium is? 3, very good. So if we're looking here at our diagram and our nucleus, that means the dark circles must be the protons and the white circles are going to be your neutrons. So how many neutrons in this lithium atom? 4, very good. And these purple or pink dots, I don't know whichever color you want to call them, how many electrons are in the lithium atom? 3, good. And our symbol for lithium is just going to be Li, very good. So our symbol is Li. Now, over in the ion, the protons are still the same. The neutrons have not changed. We have 4. But what has changed about it? How many electrons now? Only 2. So the charge on this is going to be what? So yeah, it's kind of opposite there. It's going to be a +1. This one cancels, but then we have an extra plus now. So this is a charge of +1. And this is how we write the symbol. It's going to be Li, and then in the superscript to the right, upper right corner, you just put the plus. Now, You could put 1 plus, but technically we don't do that. Like for math, do you put a 1 in front of x if it's just 1x? No, it's just x. So it's an understood 1 here, so we're not going to put the number. If you have more than 1, though, on your charge, you would designate the number. Let's look at the anions. Anions, a negative ion. These ones gain electrons. If you're gaining negative charges, you're going to become more negative. So that's why that happens there. So we're looking here at our model of our atom, this Bohr model of our atom. Obviously, it tells you it has 9 protons and 10 neutrons. Pretty easy stuff. Now let's count our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. Okay, put your little dots on there. The symbol for fluorine, does anybody know that? Yes, it is F. Fluorine is just F. Looking over here, same thing. We've got 9 protons, 10 neutrons. That's not a problem. Now count your electrons again. 1, 2, 3, 4, 5, 6, 8, 9, 10. Okay, so 10 electrons this time. So what is the charge going to be here? It's the difference between the protons minus the electrons should give you your charge, by the way. Yeah, it's going to be a -1 because it's like 9 minus 10. So we have 9 positives and 10 negatives. So obviously it's going to be a -1. And just like before, the symbol is going to be the same where you would write the F with in the upper right corner, you put the negative. And you wouldn't put 1 negative because it's an understood 1. So you would just leave it just negative. Just like X in math. You don't put a 1 in front of X if it's just, only X. Now for practice, go ahead and take 1 minute or so to try and do these examples real quick. Potassium, probably already know this though, its symbol is K. It's one of those Latin root ones that doesn't match its name at all. But when potassium loses 1 electron, it has a charge of what? Yes, exactly right, +1, very good. Now, what would our new symbol be for a potassium ion then? Yes, it would be A plus. Yes, exactly right. Good. Now let's look at the calcium example. Anybody know the symbol for calcium off the top of their head? Correct. Ca is calcium. Good. Now this case, though, it's telling us that calcium is losing 2 electrons, loses 2 of them. So what's its charge going to be? Good, +2. So now the only difference in our symbol, we're still going to have the Ca, but you add the 2 plus over here in the superscript. Now, formal charges are always written as the number and then the symbol. So 2 plus, like so. In the subscript, or superscript, excuse me, Ca2 plus. And then over here would be like the mass number and then the atomic number on that side if we were doing the full symbol. Let's look at chlorine. And I saw somebody have posted the symbol for chlorine, which is Cl. Now it's going to gain an electron. So what is its charge going to be when it gains electrons? Electron. Yes, -1. And so its symbol will just be similar to the F's where or the fluorine on the previous slide, where you just have the negative sign because it's only a -1, understood 1. But let's look at the sulfur. You may know sulfurs off the top of your head. It is S, good, and it's going to gain 2 this time. So what's the charge going to be on that? -2. So the symbol should be S with a 2 minus. So it's number and then the charge like that. That's how we write formal charges for ions. On the next slide, I'm not going to have time to go through all of it, but I did want to do the bottom row for you real quick just so you understand one with a full symbol. So here you would do the atomic number, 21, which also tells me my proton number for practice. We know the mass number over here is 45 for scandium in this particular atom, or actually ion. I know it's an ion now because it has a charge here. So the neutrons you subtract, right, and you get 24, not hard. Same old. But now we have this charge of +3. So what does that tell me? That tells me that this scandium lost 3 electrons. So if it lost, if it lost 3 electrons, how many electrons would it have at this point? Yes, only 18. And that's how you would figure out the electrons. So you can choose which one to do off of the choice board to practice. And you can do this right now or you can do it over the weekend, but remember the choice board would be due Monday. And we are done for today.